Have you ever just stopped and wondered, what is everything really made of? I mean, not the chair you're sitting on or the air you're breathing, but the fundamental tiny little bits that make up all of that stuff. This has been one of the biggest questions in science for centuries. It's like a detective story playing out on a scale that's way too small for us to see. So today, we're going to follow the clues and go on that journey.
Yeah, I'm asking you directly. What are you made of? It seems like a simple question, right? But the answer is, well, it's anything but simple. To figure it out, we've got to jump in a time machine and see how our picture of the atom, the basic building block of everything, was put together piece by fascinating piece by some of history's greatest minds.
You see, our understanding of the atom didn't just pop into existence overnight. This wasn't one single aha moment. No, this story unfolds over about 100 years, and it's marked by 4 key moments that completely flipped our view of reality on its head. Each of these dates you see here, it represents a huge breakthrough, a brand new chapter in the story of the atom.
Okay, so let's start at the beginning. Our journey kicks off in the early 1800s with an English chemist named John Dalton. Now, this guy was a game changer because he was the first to propose a truly scientific theory of the atom. He took it out of the realm of philosophy and put it right into the lab. Dalton's theory was just beautiful in its logic. He basically said, look, everything is made of these tiny particles called atoms. All the atoms of one element, say gold, are exactly the same, and they combine in these simple, fixed ratios to make compounds. Just think about water, right? It's always 2 hydrogen atoms for every 1 oxygen atom, H2O. Simple, clean, and it just worked.
So, to really picture what Dalton was thinking, just imagine a tiny, solid, indestructible billiard ball. That was it. That was the atom, the smallest possible piece of stuff you could get. And for that time, this was an absolutely revolutionary idea that brought a ton of order to the messy world of chemistry.
But here's the thing about science. It never, ever stands still. Dalton's model was awesome, but it had a problem. It couldn't explain things like static electricity. You know that little shock you get from a doorknob? If atoms were just solid, indivisible balls, where were these weird electrical charges coming from? It was a huge puzzle. Clearly, there had to be something inside the atom. And it took almost 100 years. But in 1897, a physicist named J.J. Thomson found the first major crack in Dalton's perfect little sphere.
So, Thomson discovered the electron, a teeny-tiny, negatively charged particle that was way, way smaller than a whole atom. This was huge. I mean, it proved the atom was not indivisible after all. So to make sense of this, he proposed a whole new model. He pictured the atom as this kind of sphere of positive stuff with these little negative electrons scattered throughout it to balance out the charge.
This model got a pretty memorable nickname, the plum pudding model. I know, a little old-fashioned, right? A better way for us to think about it today might be a blueberry muffin. The fluffy cake part is the spread-out positive charge, and the little blueberries are the tiny negative electrons just embedded inside.
Now, Thomson's model was a really big step forward. It brought the electron into the picture, and it explained why atoms are usually neutral. But it also raised a brand new question. Was this pudding of positive charge really how things were put together? I mean, the model felt a little flimsy, almost like an educated guess. It was definitely time to put it to the test.
And oh boy, this next part of the story is where things get really, really wild. One of Thomson's former students, a guy named Ernest Rutherford, set up an experiment to try and get a look inside the atom. He fully expected to just confirm the plum pudding model, but what he found instead, well, it was going to blow it to pieces.
Okay, so picture this. The experiment was absolutely ingenious. Rutherford's team basically built a tiny particle gun. They fired a stream of tiny, positively charged things called alpha particles, like microscopic bullets, at a sheet of gold foil that was unbelievably thin. And then they put a special screen around it to see where all these little bullets ended up.
Now, based on the whole plum pudding idea, they expected those particles to just blast right through the foil like a bullet through a piece of cake. But what actually happened was shocking. Yeah, most of them went straight through, but some of them were deflected at crazy angles. And, get this, a tiny fraction, about 1 in every 8,000, bounced almost straight back. Rutherford later said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you.
This totally bonkers result could only mean one thing. All that positive charge in an atom wasn't spread out like a pudding at all. Nope. It had to be concentrated in an incredibly small, super dense, positively charged center, which he named the nucleus. And that meant the atom is almost entirely empty space.
To really get your head around the new scale of the atom, try this.
Imagine an atom blown up to the size of a giant football stadium. The nucleus, which has almost all the mass, would be nothing more than a single marble sitting on the 50-yard line. The electrons? They'd be like little specks of dust flying around in the nosebleed seats. Everything else is just emptiness.
But wait, Rutherford's amazing discovery created a brand new and honestly, a catastrophic problem. I mean, basic physics, right? Opposites attract, so a negative electron orbiting a positive nucleus should lose energy, spiral inwards, and crash, slam into the center in less than a second. If that was true, every atom in the universe should instantly collapse. So, why don't they?
The solution to this giant puzzle came just a couple of years later, in 1913, from a Danish physicist named Niels Bohr. And he did it by taking a really radical step, bringing in some strange new ideas from this weird world called quantum mechanics.
Bohr basically said, hold on, maybe electrons can't just orbit wherever they feel like it. He proposed that they're restricted to specific fixed orbits, or energy levels, kind of like planets stuck in their paths around the sun. They can jump from a low-energy orbit to a higher one if they absorb energy, and they release that energy as a little flash of light when they fall back down. Here's a fantastic way to think about this. Picture the energy levels like steps on a staircase. An electron can be on step 1, or it can jump up to step 2. But, and this is the key, it can never exist in the empty space between the steps. Its position is quantized. It has to be on one step or another, and that's it.
And just like that, by locking electrons into these specific energy levels, they couldn't spiral into the nucleus anymore. Bohr's model had finally solved the problem of why atoms are stable. And, as a huge bonus, it also perfectly explained why different elements glow with their own unique colors when you heat them up. That light is just electrons jumping between their specific steps.
Wow. Okay, so after that incredible sprint through scientific history, from a simple solid ball to a miniature solar system run by bizarre quantum rules, what's the big takeaway here?
Let's just look at our timeline one last time, all filled in. You can see this beautiful, clear progression. We went from Dalton's solid sphere, to Thomson's plum pudding, to Rutherford's tiny nucleus, and finally to Bohr's stable energy levels. Each new idea was a direct, logical response to new evidence that poked holes in the last one.
And that, right there, gets to the absolute heart of how science really works. Those earlier models, they weren't failures, not at all. They were essential stepping stones. Each one was the best possible explanation we had with the evidence at the time. This whole story just proves that our scientific understanding is never really finished. It's always a work in progress, always being tweaked and improved. And of course, the story didn't end with Bohr, not by a long shot. Today's quantum mechanical model is even stranger and more complex. We talk about fuzzy electron clouds instead of neat orbits, and a nucleus made of even smaller things called quarks. It just goes to show that our model is still evolving. And that leaves us with one last really fascinating thought. With so much we still don't know, what fundamental puzzle about our universe will the very next discovery unlock?